Hello, I'm going to talk about the lossy distributed source coding problem with two terminals, and I talked about this problem like in another video, and I showed that for the Gaussian case, the weight distortion region, I like that, is achievable. In this video, I'm going to show that it's not just this region is achievable, but also it's tight. So I'm going to prove the converse. So again, like the problem is that like we have basically multiple sources. In this case, we just assume two sources here, and they are correlated. And you have encoders trying to do them, compress them separately, and then the decoder is going to decode them jointly. So the regions here is basically, the achievable weight region will be the intersection of these three regions here. You can see like basically for R2 is bigger than equal to 0. R2 is the weight for encoder 2 and R1 is the weight for encoder 1. So when the weight for R2 is bigger than equal to 0, then you have R1 is something like that. A little bit messy expression, and then by symmetry you have something similar for when R1 is bigger than equal to 0, R2 have something like that. And then we have the sum weight bound, basically R1 and R2 has this is bigger than equal to, there's a typo here, than this. So let's see. This one could be a pretty long video. I'll see if I need to cut it into several pieces. So first we will look at like, so we have several bounds here, right? Let's look at the first one, like the bound for R1, let's say. So basically, we have M1 is the message sent out from the encoder 1, and so NR1 has to be bigger than HM1, and by condition, conditioning reduces entropy is bigger than equal to HM1 given M2, and then we can write it as a sum of mutual information and conditional entropy. And for this one, because given x1m m1 is known, so this is equal to 0. So, and we can split this in another way. So basically the mutual information can also be split with x1m minus x7n m1 m2. And then for the second term, given m1 m2, x1 hat n is known. x1 hat n is the decoder output. So this is kind of the decoder is kind of deterministic. So with then this terms here is smaller than this one because conditioning reduces entropy. So we have a minus of that. Therefore, like this one is bigger than this one, and then we have, let's see. So this is just chain rule here. We expand that. And then again, conditioning reduces entropy. We will move all x hat and this is a vector notation, by the way. So for the whole vector, we only take x1 hat for the ith component of the x1 hat vector, and for x here, we don't care that. So then for this one, knowing x1 hat then this is just a constant. We can add this. It doesn't change the entropy here. Then again, if we remove this conditioning, then we reduces the entropy. So therefore, another bigger than equal to this is another inequality sign here. And then this one, now we only have an entropy of some random variable here. And this is essentially the distortion, right? Because this is a difference between the original from the decoder output, and the and let's say the distortion is denoted by d1i there, and also hg here is the entropy function, so this is 1/2 log 2 pi e, basically d1i here. So because Gaussian is the curve distribution have the largest entropy for the same variance, so therefore this one will be bigger than equal to this one. So therefore, because I have minus that, I have this bigger than this. Then because this log function or this hg function, you can think of this as the hg function here. This is hg d1i here. This hg function is concave. So therefore, by Jensen inequality, then this one is bigger than this, and this is just equal to d1. So the average distortion across all the across the whole vector will be just d1. So therefore, we have this. Now, if we consider nr2 is bigger than equal to hn2, m2, and then again this is bigger than the mutual information of m2 and x2, and then we can split the mutual information like this. And then the first one will be, because the source is Gaussian, is just equal to 1/2 log m 1/2 log 2 pi e. This actually missing something like similar x2 square minus x2n given m2. Now what we're going to do is we're going to write x1 and x2 in this way. So they are two just joint Gaussian variables, and we can always write joint Gaussian variables as one as the other. One as another one plus a noise, independent noise, with a scaling factor. So in this case, I will assume like this x2 and v is independent, and now we have x1. Actually, I forgot, because I forgot to mention. Sorry about that. For this one here, we'll assume that like x1 and x2 will be unit variance, and because it doesn't really matter. Like if you don't have unit variance, we can just always scale it, so it doesn't affect the result. So without loss of generality, basically what we have is the covariance of the x here is basically, maybe I write this way, is equal to 1 rho, something like that. So they have the cross correlation. The correlation coefficient is rho, and then the variance are just 1 for x1 and x2. And now coming back to here, so that's why I don't need that. That's correct. Then I need x. Okay. Then if I assume this, okay, if I write like this, then expectation of x1, x2 will be just equal to rho. That's as desired, because the correlation between x1 and x2 is supposed to be equal to rho. And x1 will be equal to rho square expectation x2. Just actually substitute this here, and v squared. This one is supposed to be equal to 1, so therefore this forces us to have the variance of v is equal to 1 minus rho square. Okay, so basically what we have is an equation like that. Basically x2 and v are independent, so therefore I can use the wait a sec. I have something I need to mention also. So basically, v and x2 are independent, because like we have basically IID here, like pairwise, like for each x1, x2. Basically, what I want to say is x1i, x2i is independent of like x1i plus 1 and x2, or like x1j, x2j. When I is not equal to j. So therefore, like we basically have the entire vector like Vn here. V is independent of x2. For each of the component, we have the whole vector Vn is independent of x2n. And then because like m2 is just a function of x2n here, this is the encoded value of the second input source. So therefore, by lemma, that actually we I show that in another video, basically that if you have something is independent of these two variables, you can write like this is independent of this given the other variable. So therefore, like we have this, and also rho plus rho x2 plus v is equal to x1. So therefore, we can apply the entropy power conditional entropy power inequality on this. So therefore, we have this is bigger than or equal to this one plus this one, and rho x squared 2 is just rho squared times this one here, and rho to the hx2 n given m2 we find that earlier is basically here, right? Yeah, it's here. So if we substitute that into here, then we have like we have this expression here basically. So then we rearranging the term, we have this. So eventually we got this. Okay. Okay. Now let's see. Now we have this, we just derive, and remember that we have in another equation here earlier, we derived that R1 something is bigger than this one. So this is the same this one here, right? So therefore we have R1, basically R1 plus this 1/2 log 2 pi e d1 is bigger than or equal to this guy here. And if we rearrange the terms, then we basically get the first inequality that we want. Basically, we have when R2 is bigger than or equal to 0, we have R1 is bigger than or equal to that. And then the second one is essentially the same by symmetry, right? So it's pretty simple to get the first two bound here, first two requirement here. The tough part is the third one, basically. So what we need is actually we need to consider two different bounds. So first one is quite conventional. There's a some-way bound, basically just considering, let's say, we are going to reconstruct x, there's x hat out of the decoder, basically. This now is a vector here, so we are going to have an estimate. So that's the x hat. Let's see. One thing I want to mention that maybe I didn't earlier is that let's see if I can find it. Oh, actually, maybe it's later on. Oh, okay, it's fine. So anyway, so let's compute it somewhere here. So we have the n r1 plus r2 is bigger than or equal to hm1 m2, is bigger than equal to the mutual information, and then we split the mutual information this way, and then okay, everything is actually kind of straightforward here. So you have this chain rule here, and this is okay. So we applied the no, actually we didn't apply the chain rule here. It's because like the pairwise ID, as I said, like we have x1, x2, like it's independent of another x1, x2 at different time instance. So you have to sum of this, and because you have these are just Gaussian, then you can compute the covariance matrix there. Maybe I use another color, it would be nice. So, and then this one, oh yeah, this one doesn't do anything. So this one now we will use chain rule here, right? So we just apply chain rule on this conditional entropy, and then again conditioning reduces entropy. You can remove this, and it will become bigger than and equal to this guy here. And then now given m1, m2, x hat, x1 hat, and x2 hat are actually kind of deterministic way. I'm thinking actually better to put a, let's see. Actually, I have an I here. Okay, actually it's correct. Actually, m1, m2, yes. And and then again, conditioning reduces entropy. We remove m1, m2 here. And here, same kind of trick as before. Like we can add now x1 hat and x2 hat here. x1 hat I and x hat 2i. Because now I'm given this guy, they are just constant. Now this difference here, actually just wi here that we just call the error here w here. So I'm not sure I emphasize that. Basically, we just write like x now is equal to x hat plus w, something like that. So therefore w is essentially the error. Okay, then this w here. So this is w. This is actually important step here. So again, this is just conditioning reduces entropy. But one thing you see that like this will be equal to this only when this error is kind of independent to your estimate, right? So and your estimate actually usually your estimate is kind of in the same space as your observation. So actually, this is what we have here is really orthogonal principle, orthogonality principle. So you have your error is perpendicular to the space of your observation, and I'm actually will use that later on. Use the fact that w is perpendicular to x hat, or like essentially it is w hat when it's optimum, when this estimate is optimum, your w, the error should be independent of x hat. So therefore we will have okay, therefore basically what's going on is if I have this, the variance is equal to something like sigma w, then because these two are independent, then this we can essentially find the covariance of sigma x hat as just like sigma x minus sigma w. We'll use this fact a lot actually afterward. So and let's see, where are we? So we are here, and then yes, and then actually this is actually bigger than equal to because like you want it to be Gaussian. If it is Gaussian, then again, like for the same variance of the covariance of the error, then Gaussian will have the largest entropy. Therefore, like this will be largest. So therefore, like this will be bigger than this. So we have a bigger than equal to sign on this way. Therefore, and then this again, like know that we are actually doing a kind of a average over like this log function here, right? But because log function is concave, we can take the average inside instead. So if we take the average inside, then we, by Jensen inequality again, then we have a bigger than equal to here. So then eventually what we have here is the distortion. It's actually is the average distortion, the covariance. So let me just write it as sigma d, and this sigma d, because we have the constraint here, the sigma d will be less than equal to, or like this less than equal to is like meaning that this s theta minus sigma d is positive definite, positive semi-definite. So and s theta here is something like that. So because we have a constraint, let's say distortion for x1 is d1, distortion for x2 is d2. The off-diagonal term can be anything, but we just write it. But of course, this covariance measure has to be symmetric, so these two terms will be the same. So it's convenient, mathematically convenient, if we write it in this form here. Then theta is essentially just the correlation coefficient, right? Kind of. So theta will have a range from -1 to 1 basically. And so anyway, this one will be less than s theta. And when we continue, we'll eventually get something like that. So what did we just done? Actually, we have basically nr1 plus r2. We just show that this is bigger than equal to sigma xx over this s theta here, and sigma xx is just 1 rho 1. The determinant is just 1 minus rho square, and s theta is just this one. So we have a bound like this. It's a rather simple bound.